Hi, I'm Christensen, and this is DECAF, Automatic Adaptive De-bloating and Hardening of COTS Firmware. This research was supported by the Office of Naval Research and was conducted by myself, Taglang and Radu, Sion of Private Machines, and Mugurel, Anghel, and Mihai Chiroiu of University Politehnica, Bucharest. So, firmware lies almost at the bottom of the stack, above only CPU microcode, and despite its extremely privileged position, it's almost entirely closed source. The delivered blobs are often at the end of a long supply chain, starting with the EDK2 open source reference implementation of UEFI, which is then taken by a company like American Megatrends, who adds the modules necessary for the specific chipset that the motherboard contains, which is then delivered to a motherboard manufacturing company like Dell or HP, who create one image for a line of products, and then finally an image for a single product. And during this entire process, modules are added but almost never removed, so you get a lot of bloat on the final blob. The code is of questionable quality, so again, it's closed source. We don't know what's going into it, but some of the code that gets analyzed or leaked or is eventually open sourced is not always so pretty. And lots of code reuse across manufacturers, across models, leads to a lot of easily replicable attacks. So Kova and Kallenberg in 2015 found that millions of motherboards were out in the wild were vulnerable to the same style of attack owing to a single module or modules being reused across manufacturers, models, etc. And many, or up to almost 70% of these modules, in our experience, are unnecessary and can be removed outright. So this is a code sample from Intel Galileo firmware, courtesy of Nikolai Schledge, who's the author of UEFI tool, which is one of the open source tools we use in this project. And as we can see here, the author of this code is fetching some value and comparing it to a constant, and later fetching a different value, but when they make the comparison, they're comparing the first value, and this happens twice. And this is the result of copy pasting, which is the kind of thing you would hope would be caught in code reviews or maybe even by a code linter. But when your code is closed source, you have no control over how many silly mistakes like this are going into your final firmware. So the way we see this is DECAF, which is a fully customizable platform for de-bloating off-the-shelf UEFI firmware. It can automatically remove up to 70% of an image by byte surface area. No source code is necessary, so it operates on the blob and uses the real motherboards for testing and validation, so no QEMU or emulation or anything like that. The functionality can be easily customized, so if you want to remove all code while still retaining the ability to boot your OS and run some application, you can do that. Or if you want to target specific features like removing VGA or USB, you can do that as well. And DECAF firmware has been running in a cloud hypervisor compute as a service environment for about 3 years now, and we found the images to be about as reliable or even more reliable than the vanilla images in terms of number of failures per instance allocation, reboot, etc. So just to go over the benefits of pruning in any blob level de-bloating scenario, not just in DECAF, what you're doing is you're removing potential vulnerabilities that we don't know about yet. So the great thing is you don't need to analyze some code and say, we found the vulnerability or anything like that. You just say we don't need it and we remove it. And then later on, if we find out there was some vulnerability, that's great. And it's important to understand that the removed code is not unused or unreachable. So oftentimes what this code is doing is it's initializing some hardware that's not actually going to be used during the firmware boot process and that the operating system contains its own drivers for. So its removal actually reduces your boot time, which is clear evidence that this code is actually active and reachable, and that if it contains an exploit, then it could have been exploited prior to its removal. And as we said before, features can be removed on demand without while retaining whatever functionality you desire. And this is a quote from a talk that Nikolai gave in 2015 at Zero Nights, where he was describing how to do a lot of what DECAF does automatically by hand. And as a motivator to the users, he said, remove all other stuff you don't want or need. If the firmware can still boot your OS, it's fine to have that component removed. Just a quick background on UEFI firmware. UEFI splits the platform installation into 4 stages. There's security, SEC, pre-EFI initialization, or PEI, driver execution environment, or DXE, boot device selection service, or BDS. And the basic building block is a module, so firmware subject volumes, and then modules, and each module usually contains a P32 executable, or at least that's what we're primarily concerned with, is the executable code. And the modules communicate via EFI protocols. So during DXE, which is the longest and for our purposes most important stage, drivers are initialized and then modules install lookup pointers to these drivers via some UID, and then other modules can look up those protocols and call into them to access the underlying hardware or to access some protocol like TCP or HTTP. And this is the primary means of intermodule communication and dependency, which will become important later when we talk about pruning. So just overview of the DECAF platform. So we use the Luigi scheduler to schedule tasks and manage dependencies. Then the firmware pruning engine, which is based off of the UEFI tool, adds modules, removes modules, whatever necessary for that specific task. And then the image is flashed by the IPMI controller onto the motherboard. The image is booted. And if it's a dependency discovery image, which we will talk more about later, then it collects some data and sends that information over the network to an external server. And then if it's a regular run, what will happen is the validation image will be loaded onto the booted image, and then some validation output will be collected. And if it's the baseline, which means the vanilla image, which is the first one to run, that data will be stored as the baseline to compare to later. And if it's a candidate image with some modules removed, that output will be compared to the baseline depending on what your validation calls for and determine whether or not to accept or reject that image. And the pruning task or the pruning pipeline happens in 2 phases. So first we take every module individually and try removing that. And then we merge the groups of modules pairwise. So if both pairs pass, then we try removing their sum. If that doesn't work, we just take the larger of those 2 pairs. And we do this until we have one candidate solution set. And then we weightedly randomly select one module at a time to add to this solution set, try removing that whole solution set. And we do that until we can't remove any more modules.
Hello, my name is Mugurel. I will be taking over from my colleague Jake. We are now discussing about dependency discovery. In the UEFI environment, the modules will communicate with each other, much like processes in a normal operating system, and this in turn will create dependencies. The dependencies can vary at runtime due to various factors, such as events in the firmware environment, such as what modules are available and what other resources are present. The module removal order becomes important to the pruning process, and this is due to the fact that a module with a lot of dependencies will most likely fail removal, while a module with no dependencies is very likely to succeed removal. In order to optimize the process, we hijack the EFI protocol API, we override the function pointers, and this in turn allows us to log all the module interaction. This information is fed into the pruning algorithm, which assigns weights based upon it. The validation is done through Docker containers. In each container, there is placed a test suite that can be easily configured by the end user. In our case, we have used DMID code to check the hardware capabilities of the platform, the LSPCI for the PCI buses, /proc/ACPI is used for the power management, and we also employ chipsec. Chipsec scans for known firmware vulnerabilities and platform misconfigurations. We must note that we do not improve any chipsec results. This is because chipsec scans for high-level vulnerabilities, such as Spectre or Meltdown, and this is not reasonable to hope fixing through just removing code. Instead, we make sure we don't remove any security-related features, such as security patch that might expose older vulnerabilities that were fixed previously. The results are quite promising. We see a boot time reduction up to 24% on both Supermicro and Sion boards. We also have implemented a feature that removes hardware capabilities from the devices, such as the USB, network stack support, various peripherals. There are many attacks that can go through these devices, such as bad USB from Black Hat in 2014. In this type of attack, inserting a malicious USB in your device could take over your operating system and even slash the firmware. We have tried to mitigate this by simply removing the USB support from a Supermicro board, and this resulted in removing 6 modules from the original. In turn, the operating system became oblivious to the existence of physical USB boards. The second part of the results shows us the net module reduction, which can vary from 9% to up to almost 70%. And we also measure the return rate in programming gadgets removed from 11% up to 62%. Please note we are using 2 flavors of DECAF, aggressive pruning and data center pruning. The difference is that data center pruning, which is in green, is more gentle with the removal process and it will retain more features such as booting over the network. Meanwhile, with red, aggressive pruning will try to remove everything that can remove while still passing the tests. Just a note to return rate in programming. This is a type of attack that employs code reusage. It chains several gadgets that are assembly sequences to execute arbitrary code. Not all gadgets are valuable. We only count high quality gadgets that we defined through what preconditions they require to be chained or what side effects they might have on stack or what operations they might also run. And we only measure those. Okay, I thank you for your attention. If you have any further questions, please do not hesitate to either contact me or Jake. You have our emails attached. Thank you and have a nice day.